Hey everybody, John here with the third part of week 1's lectures. We're going to be talking about functions. This is section 1.3 and 1.4 in your book. This is something that you should be familiar with, functions in general, and function notation, but we're going to go through that right now. So a function basically is a correspondence that takes an element from one set and puts it to another set. And usually those sets consist of numbers, and so it takes a number and turns it into another number. The important part about a function is that if I put in a certain element from set X, I will always get the same Y element every single time. There's no way to get two different outputs for the same input, and that's what makes functions work well, predictably, and it's what makes them good to work with. We want things to make sense. We don't want to put in the same value and get two different values, because then we don't know when is it going to give me this value as opposed to the other. So here's a graphical representation of some functions here. And so we just want to know, are these functions? Why or why not? Take a minute, pause the video, look at these, and determine the answer for yourself, and then unpause and see if you were right. Go ahead and pause now. All right, so looking at number 1, I am seeing this this element 1 is being mapped to both 3 and 4. Now, I don't know if I put 1 into this relationship if I'm going to get 3 or 4. And so that makes this not a function. This is not a function. And it's not a function because 1 is mapped to 2 different values. Okay? But we can still talk about the domain and range. The domain are all the input values. Now, in this case, it's a finite set. It's also discrete. And so I'm basically just going to list the elements here. And so let's go over how we do that. So for the domain for the first one here, we're going to write a set. And in that set are just going to be the numbers 1, 2, 3, 4, and 5. Now I need to write it this way with commas between them because, first of all, if I write something like 1 through 5, in math this means 1 minus 5, which is negative 4. And so this is not a symbol that means anything in math other than subtraction. Also, if I wrote 1 through 5, which I would actually do using interval notation, would look like this, 1 through 5. This represents all the values between 1 and 5, including 1 and 5. You should know interval notation. This would be all the values between 1 and 5, not including 1 or 5. And this would be not including 1 but including 5, or we can include 1 but not 5. This is how we write interval notation. But again, that's not appropriate for this problem because this denotes that we have all of the elements in between 1 and 5. So like 1.5. But that's not part of the domain here. It's just 1 and then 2 separate. That's what I mean by discrete. It's not continuous, it's discrete. So this would be the domain. The range for this non-function relation would be the set that includes 3, 4, 5, 6, and 7. Now, I know that 4 is an output twice here, but I only have to list it the one time. When talking about all the values that my function takes on, I only have to list those values one time, even if they happen more than once. Okay? So looking at number 2, let me change color here so we don't get these confused. Looking at number 2 here, it looks like every single input value has one output value. And so this is a function. the domain would be the same 1, 2, 3, 4, 5. The range is 3, 4, 5, 6. It looks like 7's listed here, but there's no arrow pointing to it. And again, 4 is hit twice, but that's okay. We only have to list it the one time here. All right. So this is just a sort of a graphical representation of what a function does. It maps one number to another number. Okay. Now, if we know that we do have a function, we can use something called function notation. So if we have a relation defined by some equation, like in this case we have a line, which we talked about in the last section, y equals 4x minus 3. This is a function, and so we can replace y with f of x. And this is pronounced f of x. And this is function notation. It does a couple different things for us. First, it lets us know that something's a function. You cannot use this notation without knowing that the thing that you're dealing with is a function. So if you see this notation, somebody has already gone through the trouble of figuring out that this thing is a function. Okay, so if you see that notation, it means you're already dealing with a function. Also, it gives us more information. Y is, it's good, but it doesn't tell us anything about the function. So first of all, if I have two equations in the same problem and I use y equals 4x minus 3 and y equals 3x plus 4, it's not as easy to distinguish between these two y's, so I could put it like a subscript y1 and y2. But with function notation, I can refer to the function by its name. So in this case, the name of this function is f, and we start with f because function starts with f. But if I had a second function, so we have f of x equals 4x minus 3, I could call it g, and g of x would be 3x plus 4. And not only does it tell me the name of the function, f or g, but it tells me the variable that I'm going to be using inside that function. What is it a function of? In this case, it's a function of x. So that's why we call it f of x. It's a function of x. I could easily, though, have a function of time, t. And then I can refer to this as f of t, and you don't have to see the rest of the equation to know that this is a function, its name is f, and the variable I'll be working with is t. And this also helps with evaluating. I can say, what is f of 3? And you would be able to tell me, oh, this is saying go to the function named f and plug the number 3 in everywhere you see the variable that we normally work with. So in this case, f of 3 would be 4 times 3 minus 3. So 12 minus 3, which is 9. So f of 3 is 9, and this represents the ordered pair 3, 9. And it's just so much better. So normally I would just have y equals 9, and I know the output is 9, but I don't know what the input is. And this notation gives me both the input f, or 3, sorry, and the output of f, which is 9. So that's why this notation is just overall better. It can be confusing, so it takes practice, just like anything else. It takes practice to get really good with function notation. But just like I'm sure when you first started learning math, this symbol was probably a weird symbol. We all know that the square root of 4 is 2, but that's just because we practiced with it. So the more you practice with a notation, the more commonplace it becomes. Just like our alphabet. When we first learned our alphabet, A, B, C, D, it was tough. But we use it so much now that we have no trouble with it. All right? So, how do I determine if something is a function just by looking at the equation? Well, I think the easiest way is to solve for y. And if you get a single equation, then the thing you're dealing with is the function. So looking at this first equation here, if I want to solve this for y, let's do it down here. 6x squared minus 3y equals 12. If I subtract 6x squared from both sides, I get negative 3y equals 12 minus 6x squared. Divide by negative 3, I get y equals 2x squared minus 4. And you can see I just have y is equal to 2x squared minus 4. So if I plug in a number like 1, I get 1 squared, which is 1, times 2, which is 2, minus 4, which is negative 2. And so I get a single value out for every input value that I put in. And that's great. So I could write this as f of x equals 2x squared minus 4. And if you are familiar with polynomials, you might know that this is a quadratic function. So now let's look at the second one, though. If I try to solve, let's do it in a different color. If I try to solve this for y, I would start by adding x squared to both sides. So I have y squared equals x squared plus 4. And now to solve for y completely, I need to square root both sides. But when I physically am the one square rooting both sides of an equation, I need a plus or minus. Because if you think about it, I could have plugged a negative 1 into here, and then when I square it, it becomes a positive 1. And I could have plugged a positive 1 into here, and when I square it, it's still a positive 1. And so I can have either the positive or the negative value that gets squared for my answer. Now you can see, now when I plug in a number like 1, 1 squared plus 4 gives me 5. And if I plug 1 into here, I'm getting both positive the square root of 5 and I'm getting negative the square root of 5. Those are two different numbers. And so I'm getting two outputs for every input, except for if I plug 0 in. If I plug 0 in here, I get 2. And just, oh no, I get plus or minus 2. There is one value in here, I think, that I will only get one output. And that's, that would be at the edge of this shape. So this is right here, y squared minus x squared. It's actually like one of the conic sections. So it looks kind of like this. And so like right here and right here, if I plugged in, if I could figure out what those points are, if I plugged those in, I would get some sort of, I would only get one value out. But for most values, I'm getting more than one out, and so this is not a function. So we have function here, we have not a function here. All right, so, or maybe this one looks like this. It's something like that. It's one of the conic sections. So it's either a hyperbola, which would be this one, or it's the two sides of this sort of quadratic parabola looking thing. All right, I will see you in the next video for the continuation of this lesson.